Hey there. Ready to really get into machine learning?
Let's do it.
We're going to go deep, explore how those machines actually learn.
Yeah, and you know what? We can make it crystal clear.
Real-world examples, no super complex math, I promise.
That's the key, breaking it down.
So are you ready to kind of unpack these concepts driving the AI revolution?
Absolutely. And the cool thing is, a lot of these ideas, they're based on pretty simple math, some going back like centuries.
Yeah. I mean, you'll be surprised, right, how relatable these ideas really are.
Exactly.
So let's start kind of the beginning.
Sure.
The perceptron. This is like the granddaddy of machine learning.
Yeah.
Invented way back in the 1950s by Frank Rosenblatt.
And you know what's fascinating about Rosenblatt? He was a psychologist, not a computer scientist.
Oh, wow.
Yet he built a machine, the Mark I perceptron, that could learn to recognize letters just by being corrected when it made a mistake.
It's like a machine learning to read. How does that even work?
Okay, imagine we're trying to figure out, like, who loves thriller movies and who, just isn't into them.
Okay, so we've got our thriller fans and our non-fans. Got it.
Right. And let's say we're considering two factors: how many hours a person spends reading every week and their average rating of thriller movies.
All right. So thriller fans versus not. How do we actually use this perceptron, this idea, to sort them?
Okay, so picture this. Each person is like a point on a graph.
Okay, I got a graph.
Hours spent reading on one axis, their average thriller rating on the other. The perceptron, its job is to find a line that, separates the thriller lovers from, the haters. We call this line a hyperplane.
So basically, the perceptron is drawing a line, trying to divide these two groups, thriller lovers on one side and non-lovers on the other.
Exactly. It starts with a random line, right? Kind of a guess, and then sees where each person falls.
Okay.
If a thriller lover ends up on the wrong side of the line, the perceptron adjusts that line to try to fix its mistake.
So it's kind of like a game of hot and cold.
Exactly. Nudging the line until it finds a good separation.
So it learns by making mistakes and then correcting the line, basically.
Precisely. And here's where it gets really interesting. The perceptron can handle way more than just two factors.
Okay.
We could add in, like, whether someone loves roller coasters, their tolerance for spicy food, you name it.
Yeah.
Anything that might give us a clue about their thriller movie preferences.
So with each new factor, we're adding another dimension. That makes it really hard to visualize, right?
Exactly. But even in these, higher dimensions, the principle stays the same. The perceptron learns from the data by adjusting the hyperplane to best separate those groups.
Okay, got it.
Now, to really understand how that adjustment happens, we got to touch on vectors.
Vectors, yes, those arrows.
From high school math.
Flashbacks, yeah.
Think of them as these arrows pointing in different directions in our data space.
Oh.
Each person's, characteristics, they become the coordinates of their arrow. The perceptron uses a math operation, the dot product, to see where each person's vector falls compared to the hyperplane.
So vectors and dot products to figure out, are you on the thriller lover side or not?
Precisely. If the dot product says, hey, this person's on the wrong side, the perceptron adjusts the weights. They define the hyperplane, basically nudging the line right in the right direction.
Okay, so that makes sense. But how do we even know? How do we know that this thing's going to find the right line? What if it gets stuck in a loop, just kind of forever adjusting and adjusting?
Yes, where the perceptron convergence theorem comes in.
Okay.
Henry David Locke, a mathematician who worked with Rosenblatt, he proved if the data can be perfectly separated by a line, the perceptron is guaranteed to find that line in a finite number of steps.
So there's a mathematical guarantee that it's actually going to work.
Exactly. And this theorem, he outlined it in a paper back in 1962. Huge breakthrough. It basically says, don't worry, if there's a solution, the perceptron will find it.
Amazing. So, okay, let's say we're using this perceptron, not for thriller lovers. Something a little bit more complex, like predicting if a patient's going to need a ventilator.
Okay.
How would that even work?
So let's say we have, 6 attributes for each patient. Age, heart rate, oxygen levels, things like that.
Right.
Each patient's a point, and now this is a 6-dimensional space.
6 dimensions.
Right, and we know which patients needed the ventilator and which didn't.
So we feed all this data, the 6-dimensional data, into the perceptron, and it's going to figure out how to separate those who needed the ventilator from those who didn't.
Yes. The perceptron's job is to find that hyperplane in 6 dimensions, adjusting the weights, nudging it until it finds a good separation. Once it's trained, we can use it to predict the outcome for a new patient.
So it goes from recognizing letters of the alphabet to predicting patient outcomes. It's
Yeah.
incredible.
Yeah.
But this story of machine learning, it doesn't stop there,
Oh,
right?
not even close.
So let's fast forward. 1959. We meet Bernard Woodrow and Ted Hoff, the guys behind the least mean squares algorithm.
But their collaboration was a total accident. Hoff, he just knocked on Woodrow's door one day, and they ended up inventing an algorithm that became, like, fundamental for training neural networks.
Wow. Talk about a productive coffee break.
Right.
So Woodrow, I hear he actually wanted to build a thinking machine, right?
He did. Dreamed big. But, the technology in the 50s, it wasn't there yet, so he focused on something more practical. Adaptive filters.
Adaptive filters?
Think about it like noise-canceling headphones.
Okay.
They learn to separate signals from noise, continuously refining their performance.
Learning from feedback.
There's that theme again.
Yeah.
Right, that's what machine learning is all about. And his work with those filters, it led him to the least mean squares algorithm.
LMS.
LMS. It uses a concept called gradient descent.
Gradient descent. Is that like finding the lowest point on a valley?
Yes. Imagine you're trying to get to the bottom of a valley. You take small steps downhill. The valley, that's the error, and the goal is to minimize it.
So this LMS algorithm is using that idea, gradient descent, to fine-tune that adaptive filter, to help it separate the signal from noise even better.
Precisely. And it's crazy to think, this algorithm inspired by noise cancellation became so important for training neural networks.
It's a good reminder that sometimes the most practical inventions can have some pretty unexpected impacts.
Exactly.
But before we go any further down that rabbit hole, we got to talk about probability and statistics, kind of two more pillars of machine learning.
For sure. And, to make things fun, let's start with a brain teaser, the Monty Hall problem.
Okay, I love a good brain teaser. Lay it on me.
All right, imagine you're on a game show. 3 doors. Behind one, a brand new car. Behind the other 2, goats. You pick a door, let's say door number 1.
Okay.
The host, they know where the car is. They open another door, door number 3, to reveal a goat. Now, do you stick with your original choice or switch to door number 2?
I feel like my brain's already starting to hurt. Feels like a 50-50 chance either way.
Yeah.
No point in switching.
That's what most people think. But surprisingly, you should always switch.
Always. But how?
Switching actually doubles your chance of winning. It all comes down to understanding how new information, in this case the host opening a door, changes those odds. It makes switching the smarter move.
So this Monty Hall problem, this is showing how understanding probabilities is key in machine learning.
Exactly. It's a great example of how our intuitions about probability they can mislead us.
Yeah.
And it highlights Bayes' theorem that helps us update our beliefs when we get new evidence.
Okay, I think I need a minute to process all that. But for now, let's move on to probability distributions.
Sure.
What are those?
Probability distributions, think of them as ways of describing, the likelihood of different outcomes for a random variable.
Okay.
Imagine flipping a coin. The probability of getting heads or tails, that's described by something called a Bernoulli distribution.
Okay, so that's straightforward, 2 outcomes. But what about something like, let's say, the distribution of heights in a population? That's not just 2 outcomes.
That's where these continuous distributions come in.
Okay.
A common one is the normal distribution, often pictured as that bell curve. It describes things like heights, weights, test scores, things that tend to cluster around an average.
Okay, got it. So we have all these different types of probability distributions. How do they all fit into the bigger picture of machine learning?
They help us create these models of the underlying patterns in the data. Those models, they're essential for making predictions and understanding the uncertainty.
So probability distributions, they're like the building blocks of machine learning.
Precisely. They help us make sense of the data, build these models that can adapt to new situations.
That's pretty cool. So we've talked about perceptrons, filters that adapt, the wild world of probability. It's really amazing how these different ideas all come together in this field of machine learning.
It is. And now we can connect these ideas to the heart of how machines actually learn. Think about it this way. All data, it comes from an underlying pattern, even if we don't know exactly what that pattern is.
So the data we actually see, it's just a glimpse of this hidden truth, this underlying pattern.
Exactly. And the job of many machine learning algorithms is to try and figure out that hidden pattern based on the data we do have. It's like trying to figure out the shape of an iceberg by just looking at the tip above the water.
And the better our algorithm can, guess that hidden pattern, the better our predictions will be.
Right. We mentioned the Bayes optimal classifier earlier.
Yeah.
It makes predictions based on that true underlying pattern.
Mm.
But usually we don't know that true pattern, so we
Right.
have to estimate it.
And that's where algorithms like the perceptron and that LMS algorithm, they come in, right? They're trying to approximate that hidden truth.
Precisely. They're trying to see the whole iceberg even though they've only got a glimpse of the tip.
That's a great analogy. So this idea of estimating patterns from data, it's been around for a while, right?
It has. A fascinating early example is the work of Frederick Mosteller and David Wallace, who were trying to figure out who wrote the Federalist Papers.
Wait, the Federalist Papers? Those essays from the 1700s.
Yep. There was this debate about whether some were written by Alexander Hamilton or James Madison. Mosteller and Wallace used this statistical approach to try to crack the code.
So they were like detectives using data as their clues.
Exactly. They analyzed how often certain words and phrases appeared in the known writings of Hamilton and Madison.
So they looked at how often they used words like, I don't know, upon or whilst.
Exactly. Based on these word frequencies, they built a statistical model to predict the authorship of those disputed papers. And guess what? They were remarkably accurate.
So even way back then, people were using data to uncover hidden patterns. That's incredible.
It is. And it shows how machine learning is really rooted in these fundamental principles of probability and statistics.
Okay, so we've got perceptrons, adaptive filters, Bayes' theorem, a bit of historical detective work. I'm curious, how do we classify data when we don't know that underlying pattern? Can you give me an example of a simple algorithm for that?
Absolutely. Let's talk about the nearest neighbor algorithm. It's surprisingly intuitive. It actually has roots going back to this 10th century Arab scientist named Alhazen.
Alhazen. Never heard of him.
He was this brilliant scholar, made big contributions to optics, astronomy, even mathematics. What's relevant for us is his work on visual perception. He believed that we recognize objects by comparing them to stuff we've seen before.
So it's like saying, I've seen something like this before, so this new thing must be similar.
Exactly. That's basically the nearest neighbor algorithm. It classifies a new data point based on its similarity to, previously labeled data.
So if we have a bunch of data points that are already classified and we get a new one, we just find the closest match and assume they're in the same category.
That's it. It's like, finding your closest neighbor in a neighborhood and assuming you probably have similar traits.
Simple but clever. But what if your nearest neighbor is a bit of an oddball? Like that one house in the neighborhood that doesn't quite fit in with all the others. Could that mess things up?
It could. That's one potential problem with using only one nearest neighbor. The algorithm can be sensitive to, noise or outliers in the data.
So how do we handle that? Do we just, ignore those outliers?
One way to make the algorithm more robust is to actually consider multiple nearest neighbors, not just one. We call this the K nearest neighbor algorithm. K is the number of neighbors we look at.
So instead of just relying on that one neighbor's opinion, you get a consensus from several neighbors.
Exactly. By averaging their opinions, we kind of reduce the influence of any one, quirky outlier.
Makes sense. But what if we've got tons of characteristics to think about? Hundreds, thousands. Finding the nearest neighbor in that giant space would be a nightmare.
That's a great point. And that leads us to another key technique in machine learning, principal component analysis, PCA for short.
PCA, okay, what's that all about?
Imagine trying to make sense of data with hundreds of characteristics per person.
Yeah.
Overwhelming. That's where PCA comes in. It helps us reduce that complexity while still keeping the most important information.
So instead of looking at all of those characteristics, we can focus on a smaller set that really capture the key differences.
Exactly. PCA helps us find those combinations of characteristics that explain most of the variation in the data, makes calculations easier, and can even boost the performance of some machine learning algorithms.
So can you give me a real-world example of how PCA is used?
Absolutely. Let's look at how Emory Brown and his team used PCA to analyze EEG signals, those brain waves they measure in hospitals. They were trying to figure out if someone was conscious or unconscious during, anesthesia.
Wow. So they're using brainwaves to know if someone's truly asleep during surgery.
Exactly. They recorded those brain waves from multiple electrodes on a person's scalp. Tons of data. PCA helped them find the principal components, basically the directions of greatest variation in that data.
So PCA is finding those patterns in the brainwaves that are most useful for distinguishing between consciousness and unconsciousness.
Precisely. They were able to really simplify the data, make it less complex without losing that critical information. That helped them build a more accurate model for predicting consciousness under anesthesia.
That's fascinating. So we've talked about perceptrons drawing lines, nearest neighbors finding similarities, and PCA simplifying complex data. I'm starting to see how all these pieces fit together. But, with the perceptron, is there a way to make it even better? What if those data points are really close to the dividing line, even if, the data is separable?
Great question. What if instead of just finding any separating line, we found the one that maximized the distance between that line and the nearest data points? That's the idea behind optimal margin classifiers.
So instead of just drawing any line to separate those thriller lovers from, the haters, we want to find the line that creates the biggest gap, kind of like the most breathing room between those two groups.
Exactly. By maximizing this margin, we're creating a buffer zone that just makes that classifier more robust, more reliable.
That makes sense. So how do we actually find this optimal margin?
That's where support vector machines come in, SVMs.
SVMs, yeah, I've heard of those.
They're a powerful type of optimal margin classifier that can handle even non-linearly separable data.
SVMs, they're like the big guns of machine learning, right?
They are very popular. Their development actually involves some really brilliant people like, Vladimir Vapnik, Isabel Gallon, and Bernhard Boser.
Tell me more about how they came together to create SVMs. It sounds like a real meeting of the minds.
It was. Vapnik, he'd been working on those optimal margin classifiers, but they only worked when the data could be separated perfectly by a line. Guyon, who was at Bell Labs at the time, she had experience with this technique called the kernel trick.
The kernel trick. Didn't we touch on that earlier? Something about projecting data into higher dimensions.
Yep. It's a clever way to transform that data into a higher dimensional space where it might become linearly separable.
So Guyon and Boser figured out how to combine Vapnik's work with this kernel trick.
That's it. And that's how SVMs were born. They're basically optimal margin classifiers that can handle more complex data by, projecting it into higher dimensions.
So SVMs, they can actually find that best separating line even in these really, really complicated spaces.
They can. And they've been super successful, used in everything from, recognizing images to filtering out spam.
So SVMs sound, almost too good to be true. Are there any downsides?
Well, like all machine learning algorithms, they do have limitations. They can be really computationally expensive to train, especially with massive data sets.
So there's always a trade-off.
Yeah.
More power, more computation.
Right.
Speaking of power, let's shift gears for a second and talk about deep learning. This is where those neural networks really start to shine, right?
Absolutely. Deep learning, it's all about using these neural networks with many layers.
And the more layers you add, the more complex patterns we can learn.
Exactly. It's like building a hierarchy of feature detectors. Each layer learning, increasingly abstract representations of the data.
But doesn't adding all those layers make the network more likely to, overfit? Memorize the training data instead of actually learning those general patterns?
That's a great question, and it brings us to this curious case of overfitting. The bias-variance trade-off. It's a fundamental challenge in machine learning.
We've mentioned the bias-variance trade-off a few times now. What makes it so important, especially in deep learning?
It highlights this balancing act, making our model complex enough to capture the details in the data, but not so complex that it only works for the data it's already seen.
So finding that sweet spot, not too simple, not too complex.
Exactly. Too simple, and it might miss those subtle patterns. Too complex, and it gets hung up on the quirks of the training data and fails when it sees new information.
So these deep neural networks, with all their layers and parameters, they should be, super prone to overfitting, right?
You'd think so. But here's where things get really interesting. Researchers have found this phenomenon they call double descent.
Double descent. That sounds intriguing.
It refers to this observation. Increasing the model complexity beyond a certain point, instead of making performance worse, can actually improve how well it generalizes to new data.
Wait, so more complex models can sometimes be better at handling new data?
It does seem counterintuitive, right?
Yeah.
It challenges our traditional understanding of the bias-variance trade-off. We're still figuring out why this happens.
So deep learning, it's full of surprises. It's like we've opened a Pandora's box of, fascinating phenomena that we're still trying to understand.
Absolutely. And that's what makes the future of machine learning so exciting. We're entering this new era where what we observe, what we see, is really driving progress, and our theories are, they're trying to keep up.
It sounds like the Wild West of AI.
It kind of is.
Researchers blazing new trails, making groundbreaking discoveries. Tell me more about this Wild West. What does the future hold?
Yeah, Yeah, it's a fascinating time. One of the big challenges we're facing right now is understanding why deep neural networks work so well, especially when they have way more parameters than data points.
That's wild. It's like trying to fit, I don't know, an elephant into a thimble.
It really is, but somehow it works. And traditional statistical learning theory, our guide for so long, is having a hard time explaining it.
So are old theories breaking down in the face of deep learning?
In a sense, yes. But it's not a bad thing, necessarily. It means we're pushing those boundaries of knowledge, making ourselves rethink those assumptions.
So are we just abandoning theory altogether? Becoming like those mad scientists mixing chemicals in a lab just to see what happens?
Not at all. Theory's still crucial. But it's playing catch-up, you could say. Empirical observations are leading the way, and theorists are working hard to develop new frameworks that can explain what we're seeing.
So it's a dynamic, that back and forth between theory and experiment, each pushing the other forward.
That's a beautiful way to put it. And this exchange is leading to amazing advancements, especially in areas like natural language processing.
Ah, yes, the world of those large language models like ChatGPT, they're popping up everywhere these days.
They are, and a big part of their success is due to a shift towards self-supervised learning, where models learn from tons of unlabeled data.
Unlabeled data. So instead of needing humans to, meticulously label every image or piece of text, these models can just learn from raw data.
Exactly. It's a complete game changer. Think about those large language models. They're trained on enormous data sets of text pulled from the internet. Their task is really simple: predict the next word in a sequence.
So it's like a supercharged autocomplete, but for whole conversations.
Precisely. And through this simple task, repeated billions of times, they develop a really sophisticated understanding of language.
Sophisticated enough to hold conversations, write poems, even generate code. It's almost unbelievable.
It is, and we're just scratching the surface of what these models can do.
It's a little unnerving, to be honest. Are we on the verge of creating machines that are smarter than us?
That's a question that's been around for a long time. No easy answers. But what is clear is that these models are raising some really profound questions about what intelligence actually is, what it means to think and learn.
It's like staring into a mirror and seeing something both familiar and totally alien.
That's a great way to put it. And as we create these AI systems more and more powerful, we have to think about the ethical implications. What are the consequences? What are the risks?
Yeah, that's crucial. We can't just blindly charge ahead without considering the potential impact. But for now, let's circle back to those core concepts of machine learning. We've covered a lot of ground.
We have. It's been quite a journey. Absolutely. It's a really crucial point.
Yeah.
As we develop these incredibly powerful AI systems, we need to be mindful of the ethical implications.
Yeah, I mean, it's one thing to create these amazing tools, but it's another thing entirely to use them responsibly.
Right? Ethics can't be an afterthought. It has to be baked into the entire process, from how we design these systems to how we deploy them.
Absolutely. We need to be asking ourselves tough questions. Like, are these algorithms fair? Are they biased? Are they amplifying existing societal inequalities?
Exactly. And are we being transparent about how these systems work? Do people understand how decisions are being made? These are not just technical questions. They're societal questions that we all need to grapple with.
It's a huge responsibility, and we can't shy away from it. But amidst all these challenges, it's important to remember the incredible potential of AI to make a positive impact.
Oh, absolutely. AI is already being used to address some of the world's most pressing problems, from developing new medical treatments to combating climate change.
It's really inspiring to see how researchers and engineers are harnessing the power of AI for good.
It is, and as this field continues to evolve, I think we'll see even more creative and innovative applications emerge, things we can't even imagine right now.
So there you have it, a whirlwind tour through the core concepts of machine learning. From those early perceptrons to the mind-blowing power of deep neural networks.
We've explored the math, the history, and even some of the philosophical questions that this field raises.
It's been a wild ride, and I hope you've come away with a deeper appreciation for the utility, the complexity, and the sheer potential of machine learning.
Me too. It's a field that's constantly evolving, full of surprises, and I can't wait to see what the future holds.
And for all of you listening out there, remember that this is just the beginning. Keep exploring, keep asking questions, and who knows, maybe you'll be the one making the next groundbreaking discovery in AI.
That's the beauty of it. Anyone can contribute to this field, and together we can shape the future of intelligent machines for the better.
Thanks for joining us on this deep dive into machine learning. Until next time. Keep those minds curious and stay tuned for more fascinating explorations into the world of AI.